lecture notes into 24 chapters, and he called it the ancient Greek hero in 24 hours. Now, obviously, you're not supposed to read the whole thing in 24 hours, but it's a really great book that's quite captivating. And the very interesting part of this experience for me is that I just read another book about Greek myth and ritual that had some completely different viewpoints from his. So it's interesting to see how two authors make pretty much the exact opposite arguments from the same body of material.
So what are the key discrepancy here?
So one of the key discrepancy was about what is myth and what is ritual. So in English, a myth is a fantastic story from the long ago past. And a ritual in English, it's something you do every day or every once in a while, a prescribed action. But for Greek religion, because Greeks and Romans aren't like Christians, right? They don't have an idea of theology. They don't have theories about God. They don't have a doctrine about what's right to believe. On the contrary, they have laws and customs that tell them what's right to do, and we call this orthopraxy. So for the Greeks and Romans, myth and ritual are a big part of religion because it helps them keep their customs. So the book I'm reading right now about Greek heroes claimed that rituals are customs and myth, the stories, are invented to explain these customs, to justify them, and they kind of feed into each other, they reinforce. But the other book was talking about basically how myth likely did not evolve out of ritual, and how how especially after the Greeks became a literate people, myth began to diverge further and further away from religious ritual. And well, I don't think they're completely opposite, because in the end you come back to this idea of customs, of customs, of explanation, of kind of social policing. But it's fascinating to see how you can kind of... Okay, so actually the book I mentioned earlier, I didn't read the whole thing. I read excerpts from it from a reader, and it was about... So there's a big difference between these two books. The one I'm reading right now was written primarily about the Greek hero. So religion is kind of a background. The author did not go into that much detail when he constructed his argument. He's simply trying to paint a backdrop against which he can explain his more concrete arguments about how heroes function in Greek society, because a big part of the function of the hero in Greek society was the hero cult. There are religions dedicated to specific heroes, Heracles to Achilles to whoever, you name it. So, and in the other book, which is primarily about religion, the author is much more meticulous. She was picking up evidence from not only the literature, but also the archaeology of Greece. Hence, you have two very different writing styles. But
great. That's good. That's good to compare. Yeah, that's good to compare that way. I think it's really provide better perspectives. Okay, so let's go back to our class. And so first of all, let me ask you, and how many of you are able to so basically you were not completely lost and you are able to follow, or you are still interested in this class? I mean, that's something I worry. And I could teach different way or different stuff, and but I do need your feedback before I jump too fast. So any of your comments or feedback will be very, very important, because this is not simply just teaching, and I would like you involve, participate in, and offer your feedback and suggestions and whatever. So because there's so many so much material I could teach, and math, physics, and astronomy, and many different things, and I could shift the focus away from too much math-oriented physics to less math-oriented physics, or other things. But I do need your feedback. So if you think it's this way, it's go this way, you learn something, that's good. If you think this is probably not very efficient way for you to learn, or it's completely you're in dark, you should let me know. Okay. There any comments right now?
Well, I feel like I learned a lot so far, and I don't really I'm fine with going to another topic or staying on math. I'm fine with both.
You're fine with both, and okay. And how about other people? Can each of you just offer a quick feedback, saying where are you? And because I noticed, for example, like in the past 2 lectures recordings, and only a couple people viewed them. So therefore, my understanding is not most of you didn't really watch again, which indicate you probably you think you are lost, or you think you didn't want to completely follow any. So it's, of course, it's okay if you just think, oh, I can just sit in the class, listen, and I get something, right? No matter it's 50% or 70% or 30%, that's good for me for now. So that is one way you deal with this lecture or seminar. Another way is you want to really try to understand as much you can, then you probably have to go back to review the material, right? So I don't know each of you what your where are you, where were you? Do you mind each of you just talk a little bit about share about your feedback, your comments or suggestions? Hello? Hello? Anybody there? How about at juncture, and you can go first.
Oh, wait, what? Okay. Well, to be honest, I did not get time to go back and review any of the lectures. I feel like I am interested in the course material, and I believe I followed along when we were doing the math. But I think I need to go back a little bit when we were working with the Newtonian stuff, and I feel like kind of my lack of comprehension is my own fault for not really checking back on things. And yeah, I think I like the course and I like how it's taught.
And how about Sincere?
I think like I can really follow like what we're learning right now, and like I liked what we're learning right now, and I think that I should also like go back and see the recordings about the things. Yeah.
Okay. And but you think you've continued current way, you're okay? Oh.
Yeah.
Okay.
I'm okay with this right now.
Leo?
Can you hear me?
Yeah.
Okay, I can follow along because I've learned these stuff. So
Okay,
it's
so
not
you are good, right?
yeah.
Okay.
But
And
actually, I'd like it to be a bit like more sort of like interdisciplinary instead of just like math and science, because like we obviously developed like a perspective of science, but I'd like we to like talk more about like how it connects with like, say, social science or politics or like, you know, literature or history.
oh, you
Just
want to,
saying.
okay, multidiscipline go. Okay, sure. And Jenny?
Yeah, I think the course is all right. I can keep up with it. Like, it's okay.
Okay. You do have any wish, or like Leo wish to be more interdisciplinary, or try to link with, go beyond just the math and the physics, I guess, and to try to link with maybe a story, applications, and the history, and all those, yeah.
I don't mind. I can go either way.
Either way, okay. I think we lost somebody. Who were on and we lost? Oh, Bill were on. We lost him. But okay. Anyway, so let me continue. Yeah, I will keep asking based on your feedback, and so I hope the real purpose really you guys can benefit, right? Otherwise, there's no really purpose for here. Okay. You are able to see my screen now?
Yep.
Okay, good. So basically, let me go review what we went through last time. And so what we went through last time is basically, let's focus. Yeah. So what we went through last time is basically talking about is just like a two-dimensional and the movement situation. And we are go back to very general situation is like using a polar coordinates and try to, in the really general case, try to derive the relationship between angle velocity and velocity and acceleration and so on, right? So that's it. So basically in this no matter in this top is really the XY coordinate system, right? It's pretty simple. You split into decompose into X direction, Y direction, and then you just do the derivative and you get velocity and acceleration along both direction, X direction, Y direction. And then of course you get the amplitude is just using this relationship. So that's pretty much it. And but go into polar coordinates, which is the R and the theta configuration. And in that case, the position vector can be described in again decomposed in XY direction, but is based on the polar coordinate R and theta. So R cosine theta, which is X, and then R sine theta, which is Y in terms of the position, right? Vectors. And then you're going to define the velocity is dr dt, and then you do just based on the math, based on the calculus, you can apply the derivative into individual, and eventually you get basically under this kind of coordinate, the velocity is written in this kind of form, right? And then you continue on derive of dv dt, which is the second derivative of dr dt. And in that case, you can continue just so the reason I do this is I just try to apply math and a little bit of physics by definition, and we can get pretty general. For example, this is very general dr dt, I mean the the dv dt, the acceleration form. It is a very general case, which is in any of the two-dimensional movement, as long as you can describe in this kind of you can always describe in this kind of configuration, and then you can always get this this acceleration that way. So I was trying to say now I can get the idea that linear velocity for the circular motion is really the angular velocity time r. You learn that quickly from here, right? So it's very easy from here to get that concept. And then for the circular motion, which means r is fixed, in that case, your linear acceleration is angular velocity squared time r, or linear velocity squared time divided by r. So that is linear acceleration, or the acceleration. So now my question to you is, do you ever think about it? So why I have a constant linear velocity doing a circular motion? Why I have acceleration? So my speed amplitude doesn't change, right? If you are just a spin around a circle with a constant linear velocity, which is v, and really means if the r is constant, then angular velocity is also constant, your linear velocity is constant. In this case, why I have a acceleration? Right? This is a little bit of physics. This is not math anymore. Okay, why is that?
Because the direction of velocity is changing.
Correct. So that's linear is right. So basically, don't forget, in physics term, let's say we are doing a circular one, even though my radius is fixed and I'm rotating around the center at a constant angular velocity omega, which means my linear velocity is r times omega, right? Which is also constant, which really means no matter is, per second I move 5 meters or 1 meter or 1 centimeter, this is never change. I go in this circling around. But why I have a velocity, right? So if you just saying if a velocity is dv dt, so v doesn't change in amplitude, in magnitude, therefore that should be 0. So why I have, you are saying why a is omega squared time r, or v squared time divided by r. Why? So just like Leo explained, don't forget, this is not correct. This is wrong. If you go by a straight line, this is a straight line moving along a straight line. This is correct. However, when you're not really going straight, going a changing direction, so the acceleration is really the vector change. So in this case, even the v is a v constant amplitude. However, the direction is keep changing. In this case, say if you're moving to here, then same v equals r omega is now is, for example, at the top of the, at the top of this circle is moving to left, at the bottom of the circle is moving to right, here is moving to up, and here's moving down, right? Here's moving maybe like 45 degrees from the vertical. So it's always keep changing the direction. So that because changing direction, so really means v vector is changing. That's why you have acceleration. You don't have, it's not like this. It's not just about amplitude. It's also about angle, which is perfectly reflect in this circular motion, right? If you really look at here, if we just go by, say, we change the time by little bit, right? So you are seeing this one changing an angle by little bit. So if you zoom in, right? So this is my R. So right now I have a which is always perpendicular to the velocity, right? Perpendicular direction to my radium. And then now I'm moving to this position now after a little bit of time. And then now direction is also perpendicular to my radium. So if you really look at those two velocity, you put them together and you shift them, come over. One is initially is this direction, then later on becomes this direction, even though they are same amplitude. And so therefore, the difference between those two is like this. Understand? So this is the initial V1, right? With the direction, which is towards this direction, now become a little bit V2 after a little bit time, becomes this direction within the small delta t time frame. And now the difference between those two actually is going this way. Actually, you can see it as actually going towards the center, this delta V. So that is why the acceleration is always facing the center. Got it? If you really look at it here. So you can do this way. So that is actually in your general physics teaching, which obvious do not follow the way I present the physics to you. So this is how in the textbook explain the circular motion is basically drawing this kind of curve and this kind of delta theta, right? Delta theta is omega time delta t, angular velocity time little bit time. You rotate this kind of delta theta, then in that case you can use trig or use geometry to calculate the change of delta V. Then you can leading to give you this formula. You can derive this formula this way. Okay, got it? So that's how you may want to go back to use the, this typically in all the high school textbook talking about angular motion is always derived this way. Just just to try and say, oh, this is at the time t, I have this position, and at the t plus delta t, I have this position, and the change of the velocity is this change, and this change. This is delta theta, therefore here is also delta theta, right? Here is also delta theta, right? Delta theta, and if the V is, this is V, this both are V. So basically you are having a V, and the change of delta V and is really delta theta. So therefore delta V equals V times delta theta. Correct? And so in that case, you will see A is now is delta V times delta T, which is V delta theta times delta T, and the delta theta time divide delta T is omega. So now is V times omega, which is R omega squared, or V squared divided by R. So that quickly you can derive this quickly derive this simple relationship, like I derived from simplified very general case, right? This is a way the textbook in your high school textbook always to derive y is V squared divided by R times omega squared is simply like that, right? I didn't go to this direction to derive it, but I went to the more general format, right? So you can see the correlation between those two. I hope you now understand a little bit better from a physics concept. Even though math is very important in physics, right? As I have demonstrated to you, right? With a powerful calculus, you can do lots of things you couldn't do without the math tool. But even though the physics concept has to be crystal clear, That's why I go back to try to explain why the velocity amplitude doesn't change and constantly linear motion rotation. So why there is a velocity acceleration, and why the acceleration actually is always going towards the center, like the 向心力、离心力. So why is that case? So now I explain to you, right? So this is small explanation, but this is actually is a little bit of physics. And the note, so when we trying to use fancy math tool to derive those general formula, which is great. The reason I go that path, I want to prove to you the physics is quite simple once you have math tool. But however, you have to constantly ask yourself, do not get lost in physics concept, right? Concept is important. If you couldn't answer the question like why the linear velocity is constant along the rotation, why there's acceleration. If people say, oh, dy dt doesn't change, therefore should be 0. Why you are saying v squared divided by r? So if you cannot answer this question, really means your physics concept is not there yet. Okay, so this is a physics concept, very important. Okay, this is just a quick review of this material. Hopefully you can have understand it better. Actually, if you really curious looking into this general form, acceleration under the general situation really means even like the radium is changing with time, and angular velocity and it also changing. Therefore, there's angular acceleration situation, and all this kind of very general general situation. There is called this one actually can explain. I can have separate conversation about this. Explain why we are on Earth's surface, right? We are in the north hemisphere. Why we flash toilet? The toilet is always going spin. Which direction do you know when we flash toilet? Or we in a sink we let the water go, so the water starting to spin. Which direction is spin? Anybody know? When you go to the south hemisphere, is a reverse direction. Anybody know why? Actually, everything is here in this. This is called Kirchhoff's force, 克里力. Actually, is coming related to one of the term here, and then so that can explain why when we are on the north, we are on the Earth's surface. Earth is spinning, right? And when we are moving on a spinning Earth, and we will get one additional acceleration coming from here, which is let the water in the sink spin. Why the tornado also spin? Why the tornado spin? The clouds and the rain clouds spinning, and on the river you see the water spin, and in our toilet, when you flush toilet, water spin. So everything is related to here. Okay. So that's part of the physics here. So okay. So this is one I try to explain to you here. So now the next I want to talk a little bit about, go back to our orbiting, right? We know the Earth, we know the Earth orbiting Sun and Moon orbiting the Earth. So let's do a quick calculation based on what we have learned. So what we have learned so far is when we do with around the center, we will do a circular motion, right? Let's say with a constant linear velocity, linear speed, and let's v, and here is radium r. So in this kind of circular motion, we have the acceleration is v squared divided by r, or you can see r times omega squared. Omega is angular velocity, v is linear velocity, and r is radian of the circular motion. So in this case, this is one of the good important relation. Same thing also, v equals r times omega. So those two are the circular motion important formula relationship you need to know. And once you know this, we can do all sort of quick calculation. For example, how about let's calculate Mond orbiting period around Earth, right? So in this case, we have Earth is sitting here, and the Moon is sitting here, and the Moon is orbiting around the Earth. The Frank is coming. So so basically, this orbiting, now we have the distance between Earth and the Moon, right? So with this kind of relationship, now we can do this calculation. Let's calculate the orbiting period. Or we know the orbiting period, we could potentially calculating other parameter like the mass of the Moon, or the radians. Some other parameter you can derive the one of them. So this is basically, let's do that, right? Frank, are you on?
Yes, Dr. Wang. So sorry I missed the beginning part.
No problem. Yeah. Beginning, we were just I just quickly for your benefits, also never mind, we can. So basically, beginning, I was trying to review what we did last time based on a polar parameters and the very general case of derived dv dt and dr. I mean dv dt and dr dt, basically velocity and acceleration. And so have this very general form. And now I try to ask a simple question is try to test how, even though we use very powerful math, but I don't want to lost the physics concept. Therefore, I was asking with a simple circular motion with a constant linear velocity, v equals rw, which really means the angular velocity also constant. In this case, we were saying that our acceleration is omega squared times r, or v squared divided by r. So I was asking the group, if we know the acceleration is where the changing rate of velocity, a equal dv dt, since the linear velocity v doesn't change, is constant, when rotating, no matter it's a 5 meters per second or 1 meter per second. So shouldn't it be dv dt equal to 0? So why we are saying a equals v squared divided by r, there's acceleration if the linear velocity doesn't change in amplitude, right? So this is more like asking how whether you truly understand the physics definition, because this is completely wrong. Because in this case of nonlinear motion, the acceleration is not really amplitude by divided in derivative to time. It's rather is a vector, the changing. Because this case, anytime the direction is keep changing, even though amplitude doesn't change, directly change. Therefore, it is not a constant state. It's a changing state. Therefore, there's always acceleration associated with that. So then I try to quickly derive what the textbook does in your high school teach, because your high school do not use the way I derive the formula, and I was trying to use more powerful calculus. But here in the high school math physics teaching is basically here's r radians, velocity at this moment is v, and after delta t time, the rotated by delta theta, and so you change direction. So therefore, you are doing the dv, and which you can quickly using amplitude, I mean, you can quickly derive this formula by this way. This is basically, I'm confident your high school when you derive a circular motion, how to get this formula is using this way, right? So this is how you explain rather than using the calculus I went through was very general form, right? So I will try to, we talk about this a little bit. And meanwhile, I was giving even additional comments about how powerful this method is. I gave a very general acceleration for the two-dimensional case. In this formula, if you are serious, we can give a separate talk about called Kirchhoff's force. It's basically that's explain why on Earth is spinning on Earth's surface, depending you are in the north hemisphere or south hemisphere. When we are when we have a velocity move, then we will feel another force, another acceleration is called Kirchhoff's force, and that is explained why the water spinning when we dunk the water in the toilet, flush toilet, the water spin either clockwise, anti-clockwise, depending where you are on the Earth's north or south hemisphere. So that is explained perfectly in here. Okay. So that's what I just you missed part, and then I was saying I was correctly try to do a little bit of calculation estimate. So using what we learn, if it's constant linear rotation around a fixed radian, so we know the acceleration is v squared divided by r, or r times omega square. We already know that from we already just derived. And the linear velocity equals angular velocity time radian. If we know this, I want to do go back to our astronomy, saying that what is our orbiting period around the Earth for Moon? We can quickly do that. Let's do that. Okay. Then we also want to do center is the sun, and our Earth orbiting around the sun. So let's do this two case calculation. Sometimes working with physics actually is very important. Play with some number. So that is how you learn. You get a sense about physics, right? So, a strong recommendation for you is along you learn physics, sitting down, take a piece of paper, take a pen, and try to do some, using your physics knowledge, do some, even though it's very rough estimate or calculation, so that help you enhance your physics sense. And this is very important. If you want to be a good physicist, we always have a very strong physics sense. That is how help you to identify problem and help you to solve problem. But this kind of sense need to build on some of those kind of quick, we call the order of magnitude kind of estimate. Okay, but this one, let's do that. So basically here we have the Moon orbiting around the Earth for the first situation of Earth are orbiting around the Sun. In that case, we know the mass. For example, Earth we call ME, mass of Moon we call MM. Okay, ME. We know the distance is r. So we know the velocity here is v, linear velocity, let's assume, and orbiting around here. So how we do that? So we know the force between the two subjects based on the universal gravitation. We have hinted before. This is a same kind of fundamental rule like Newton's second law, right? Newton's second law is F equals ma. And the Newton's universal gravitational law is F equal to G is a gravitational constant, and the time the mass of two objects, and the time multiplied together divided by distance squared. Okay, so this is so basically we link those two, we'll be able to derive what we want. So let's do that. So basically now we have in Earth Moon case, we have G, which is constant. I will tell you the value later. And then we have we have a big mass, mass is Earth, small mass is Moon, and divided by the Earth-Moon distance square equals to F. F, this is F, which is a traction force between those two, right, along their linear, their direction, right? For Moon is attracting to this direction, for Earth being tracked to this direction, okay, attract towards each other. So, and then the F equals ma. So this m is the, because this is the Moon orbiting around Earth, this is a Moon mass. Velocity, acceleration we know is the v squared divided r. R is Earth-Moon distance. V squared divided by r. Okay, so you have this one. You see the both sides we have mass of the Moon, which will be cancelled out. Therefore, this orbiting doesn't really depending on the mass of this orbiting object. It will be cancelled out. So from here, we can derive V equals to basically G m of the center mass, which is Earth, divided by r distance between the two. So that is what we get. Okay. Now, how we get to the period? We want to know how long for Moon to orbiting around Earth for one circle, one round, which we roughly know is what? Everybody should know, right? How long Moon orbiting around Earth for one circle? That's
like
what we call
days.
Yeah, we call the month, right? The month. And so let's see whether that is close to 30 days, right? So that's what we can calculate. So this one should be, because when we go around one circle, the circumference is 2 pi r, right? And so let's put this way. So the linear velocity is really this. The linear velocity should be 2 pi r, go through one circle. Total time, we know the linear velocity, which is what we have here. So in that case, if these two equal together, so that give you t equals to 2 pi times r divided by v, 2 pi, yeah, t equals 2 pi divided by v. You put v into here, the 2 pi basically square root. Now r become r cubic, because if I put r back into the square root, and then the gm, right? So that is our formula, okay? Correct? So in that case, let's put in the number, and the g is gravity constant, is a physics constant we know really well. This one is 6.67. I always use SI international unit. So that's why 10 to minus 11 Newton meter square divided by kilogram square. Okay, this is G. And our Earth's mass is 5.97 times 10 to 24 kilogram. That is our mass of the Earth. And our average, even though Moon around Earth actually is not a perfect circle, it's pretty close. So the average, this is average radians. Okay, we use average radian here, is roughly, this is one equal to, you can find the number 3.84 times 10 to 8 meter. Okay, those are the three things we need to know. We can put it back into here. We can calculate the t for the Moon around the Earth. And this one, if you do, it give you like 2368,147.82 seconds. Okay, this is the period of orbiting. Then you divide this one by 60 seconds becomes a minute, 60 minutes becomes the day, becomes the hour, divide more 24, divide all those become day. So this one eventually you can see is 27.4 days by this what cover calculation or estimate. So that is our month. Okay, typically we say it's 28. Okay, Chinese month, not Western month. Okay, so that is orbiting period. So you understand why is it 28? Why is it 28? Because 28 are lunar months. Lunar months actually follow the orbiting period more closely to the Western month. Okay, this can go back to history. And Leo talking about the interdisciplinary. We can do a search about how this month concept come historically and who is more correct. And why we are now 30 days, not 28 days, something like that. There's a we can talk about it later. Okay, so this is
Well,
go ahead.
At this time, Einstein gonna jump out and argue that the moon is actually moving in a straight line in a distorted space-time.
Yeah. So then, Einstein were, the general relativity will argue that actually we are fall into this kind of space-time warp, right? Yeah.
Yep.
So because in the general relativity, what Leo inferred to is basically the gravitation force is actually is a space warp, space-time warp.
Right.
Yeah. So that is Einstein's general relativity theory. Try to explain. So this is a good question actually. Studying physics is trying to understand everything happen around us, right? And try to explain them from a most fundamental principle, right? That's the dream of all physicists, all the scientists, because that's why people saying, do we have one of the universal formula which can use it to describe everything? Just like when Newton have F equals ma.
E is equal to mc squared.
So when Newton have F equal ma, he was so proud. It was so powerful because he can do this kind of calculation and coming with basically let's finish. So if we go back to the Sun Earth case. You use the sun math and Earth to Sun average radian. In that way, you can find online as well. So this way give you T is about 31,555,495 seconds something. So this one you convert it into days, become 365.23 days. Okay, that's our year. Okay. But anyway, so go back to our discussion. So basically, we were saying that physicists trying to simplify, well, it's not called really simplified, but try to grab the most essential concept of working principle for the whole universe, and which of course governing how the apple fall from tree and how the earth fall towards a sun and how the universe work, and meanwhile not only those kind of gigantic object, but also down to atom, down to quarks, down to molecule level. And so physicists have a dream trying to use one theory and one formula try to explain everything. That's an extreme dream, a simpler version of the dream. And however, in the past thousands of years, and we are marching towards that dream. And of course, along the way, we have F equals ma, and Isaac Newton once said, "Give me a lever, I can move the whole universe, move the planet." So he was saying how powerful his F equal ma is. Unfortunately, F equal ma even though we can explain this kind of thing perfectly, but we couldn't use F equal ma applied to electron, to electron orbiting. For example, here is an Earth and the Sun, orbiting, Earth, Moon orbiting around the Earth and Sun or Earth. But meanwhile, we know in the hydrogen atom we have a nuclear, and then we have electron orbiting around the nuclear. This is hydrogen.
It's not a particle now; it's a wave here.
Right. This is a hydrogen atom, concept, right? And it was tiny, right? This whole thing is only about 1 astron, which really means only about 10 to minus 10 meter in diameter, this size. Okay. In this kind of case, of course, electron mass is so small, right? And 1,000th of the nuclear in terms of mass, and orbiting around the mass. But here, the orbiting is quite different from this orbiting concept. In our, universe orbiting concept, Earth is, repeatedly billion years, like going around circle by circle, fixed trajectory. That's why we can predict precisely down to sub-second about, moon, sun, lunar, or solar eclipse, so on. But in the electron case, F equals ma failed terribly. There's no way use F equal ma to calculate where electron is at any moment. So that's a failure of Newton's law down to atomic scale, right? So that eventually invented quantum mechanics. We can talk about later. So why there's quantum mechanics? And then quantum mechanics failed again when we go into the nuclear, inside the nuclear, talking about quark. Quantum mechanics failed again. So therefore, physics trying to constantly improving the theory. So whether we are able to explain the whole universe down from the sub-quark all the way to the the gigantic galaxy, do we have a unified theory? A set of formula able to explain everything? Doesn't matter what kind of size it is. Of course, this size, I think one of the talk I mentioned, this size scale varies probably 10 to 100 times power from the smallest one to the biggest scale. No matter as a time, as a physical dimension, whatever. This is a universe. This kind of scale difference. So can we, across this kind of scale difference, we can use a unified theory to explain everything? As of today, we are still not there, okay? Yeah, we're still fighting for a unified theory. But we made tremendous progress as a science, as a community, towards lots of understanding, so step by step, right? So we have this Newton law perfectly predict the period, and we have quantum mechanics perfectly predict for example, the hydrogen atom. When hydrogen atom was heat up or bombarded by something, going to emit some light, or hydrogen atom, cold hydrogen atom, going to, when sun passed the hydrogen atom gas cloud, and we found some sharp absorption dark line within the solar spectrum, which originally should be continuous, and so we found sharp dark line. So those lines has a precise position, and we can use quantum mechanics precisely know which location those solar line is, those absorption line is. So that's indicate how powerful like quantum mechanics is. However, there's between the quantum mechanics try to explain the hydrogen atom and the hydrogen spectrum, and from the Newton law is still able to explain perfectly about the orbiting of the planet towards the solar. So that's a gigantic scale where different theories. So we're still trying to find a unified thing. Okay.
Wait, so question.
Go ahead.
So obviously, like Newton's law, well, because like based on the quantum world, it can like completely override the Newton's law. But like the Newton's law is still like sort of makes sense in our day-to-day life as we observe, is because it sort of takes the perceivable part of the quantum. So like you know, in like the quantum waves, everything is described as waves, but in the Newton world where everything is described as particles, the particles is essentially like the sort of like the peak of the waves that's like detectable, whereas like the other part of the waves is too small to make a difference in like a macro level, but it's
that's a simple very simplest. This is what you said is very simplest trying to understand this, which is okay. So ideally, you hope you have a unified theory or formula, right? And so this one can apply to hydrogen atom and universe scale. So those scale could be crossed 10 to 100 power 100 times of order difference. So what we try to say is we have a formula which, when we apply to this case, we can approximate to eventually Newton law. When we use this one towards small scale, so we can approximately eventually leading to Schrödinger equation of quantum mechanics. So this is what we are looking for. You know what I mean?
Okay.
Yeah. So we know that F equals ma because we can predict so well, so must be correct and under certain approximation. We know quantum mechanics also correct because otherwise they cannot predict random, like hydrogen jump, hydrogen electron jump give the spectrum, absorption spectrum. So, but it can predict precisely, and therefore meaning that it is correct under that kind of scenario, right? So now the question is, do we able to find a theory in the general unified theory able to say, oh, under one scenario, it can be simplified eventually as F equal ma. On another situation, simplified eventually to be the quantum formula, Schrödinger equation. So where are we in term here, right? So this is right now people call the super string theory and unifying theory, and trying to approaching to that, but we are not there yet. Okay, but we made a tremendous progress, right? But we are still not there yet. Okay, got it. So that's a little bit conversation about this, and let me see what's next I like to talk about. Any other question or comments so far? I like to maybe let's talk about I suppose talk about this one later, but maybe we should do it now. Yeah, let's talk about the black hole. Okay, it's all related to here. It's so let's talk about a little bit about the black hole using the last we still have 40 minutes. So let's talk about the black hole. So basically, I'm saying we can also derive a black hole situation like this. So do everybody know what is black hole, right? Black hole. So even though like black hole is basically we believe it exists in the universe somewhere, and so when the star die out, eventually can turn into a black hole, and it's a small, highly dense stuff. I will give you quantum idea later. Is in this kind of black hole, basically anything where cannot get out, including light. Okay, so anything fall into a certain radius from the center of the black hole.
The field is too big.
Yeah, it's basically like you just be sucked in, including light, including photon, we call the light. Light will be sucked in also, cannot get out. Okay. This is called black hole, right? So let's do using the limited physics we have learned, say try to understand black hole. So let's say we have this is our black hole, and its mass is huge, it's m, and radium is r. Okay, it's black hole. And now how to define the black hole? Because we know the fastest things can move is light speed. This is another conversation I'm going to talk about later about the light. Okay, light or photon. So let's utilize this knowledge. So light is travel with a speed called light speed is c, roughly 3 times 10 to a power 8 meter per second in vacuum. Okay, in vacuum or in air. In air is pretty much closed vacuum. So that is light speed. So anything with mass electron cannot travel to light speed. Only light has no static mass. Only light or electromagnetic wave can travel light speed. So nothing can travel faster than light speed. Okay, we can talk about this later, but let's assume that's the case. There's a light speed. And so basically, so photon is light is basically travel this light speed. Since the light, this photon, which is a unit of light, a particle of light, so photon cannot get out of the black hole. So we can use this simple, say, under what condition photon, what size mass condition, the photon cannot get out of black hole and escape black hole, then we can derive the black hole relationship between mass and the radium and so on. So that's what we try to do in the next, hopefully, yeah. So basically here, so we consider photon, right? Photon on the surface or any particle on the surface of the black hole try to get out, escape from the black hole. So really, then we typically looking into energy configuration. So this energy we know is called, there's a kinetic energy m of 1/2 mv squared, right? And there is called a potential energy when a particle small m and at a distance from a gravitational center, this energy is related to the, basically this energy is did I derive that before? So basically is this energy is basically gravitational force, which is gmm divided by r squared time a distance time r time distance. Therefore, the energy form is gmm divided by r. Okay, so this is energy. We call it potential energy, right? So this is a kinetic energy, potential energy. Potential energy is typically we say is negative because we think the infinite away, the r equals to infinite. This part becomes to 0. So here is 0, and everything else close to the surface become negative. Okay. So this is a total energy conservation. So if this particle able to escape the black hole, really means the particle able to travel infinite away from black hole. In that case, the potential energy will be 0, right? And let's say this particle travel away because at being absorbed, attracted by the black hole through the interaction force or gravitational force. Therefore, so it will slow down, and eventually finally reach infinite away from the from the black hole, and the speed already reduced to zero, or pretty close to zero. Therefore, it's able to escape. So that's escape. So therefore, this one eventually becomes zero, right? So potential energy infinite away, zero. Speed is also zero, able to escape. So this case is derived. We call it escape velocity. So this is a way we typically derive any, for example, Earth has also an escape velocity. Sun has an escape velocity. Really means when we shoot a satellite, shoot something, if we want to let it orbiting around the Earth, then we need some speed. Because if speed not high enough, we are going to fall back to the Earth's surface. When your speed is strong enough to go away, go further away before falling down, eventually able to circulate around the Earth. That's called the orbiting speed, which we already derived, right? The one we use to calculate the moon and the Earth period is using that orbiting speed. But if we speed further away, further speed, eventually this guy could go, could basically escape from the Earth or Sun to become of, for example, try to leave the Earth control regime or leave the Sun control regime, which means the our solar system. So, but you need enough speed. So this speed is calculated by this kind of relationship. Okay, so this is the minimum speed you need in order to escape. So from here, V equals to G small m canceled, bigger M is 2 divided by R. So this is escape speed. Remember the orbiting speed, if you remember, is this relationship. This orbiting speed we use to calculate the orbiting period we just did. Yeah. So this is we use to calculate orbiting period. This is this orbiting speed. Okay, V equal Gm divided by R square root. So which is here. Okay. You see the escape velocity is square root 2 time of this one. It's bigger. So bigger you can escape. Okay, so you need this speed in order to able to get into the orbiting orbit. You need this speed in order to you need to reach this speed in order to be able to orbiting around the Earth. You need to get to this speed in order to get away, escape from the Earth. Okay. Okay, so let's go. Black hole really means that light, which travels in velocity of c, is able to barely escape or couldn't escape. In that case, really means the velocity here is c. So that gives you a black hole relationship, which is another very famous formula called the Schwarzschild formula. So basically here you have c, light speed become your escaping speed. Okay, so this way you have this formula. So this way give you basically R black hole radium equals to 2gm divided by c squared. Okay, so this is black hole relationship, famous called Schwarzschild formula. Okay, simple derive is this. Any questions so far?
Yes.
Go ahead.
Okay, so we talked about how like light cannot get away, sort of like needs to reach this speed to get away from like the black hole because like because we use like the Newton model in which like the huge black hole is supermassive and it has like a lot of sort of like a very huge gravitational force, and in this case light is perceived as particles, right?
Correct. Yeah.
Okay, so like in the Newton world everything has to be perceived with particles, and in like the quantum world everything is wave. We can't just like mix it up, so like
Correct.
something is particle and something is wave.
So yeah, good question, Leo. So photon, right? Photon itself is basically particle description, right? Correct. Yeah. So photon photon, for light photon, we can talk about this later. The energy of photon equals to Planck constant time of frequency, or Planck constant time light speed divided by wavelengths. Okay, we can talk about this later. So this is formula. So this formula, and so we see that electromagnetic wave or photon has no static mass. So it really means photon cannot be still. Photon has to always travel with light speed. Okay. So the photon's static mass is, we call it 0. So photon has no static mass. Okay. So because it cannot be standing still, okay? Yeah. And however, doesn't mean photon has no mass. People say photon has no mass. Yes, it's really referred to as no static mass, but it does have mass from the you know the famous E equals mc squared, right? Yeah. So any energy has mass because energy and mass relationship. Okay, so therefore you can derive E equal mc squared if E is photon, which is at h mu or hc divided by lambda. You can derive what is the mass of photon. Mass of photon is basically h. So you give me the wavelength of you give me. Kevin is knocked out. So you give me the wavelength of any light, and so a Planck constant is there, light speed constant is there, so I know the mass. But this mass is not static mass, is called you know, the dynamic mass. You understand? So you can use this mass to do the GMM R squared gravitational with anything. Photon, Earth, or photon, or sun, photon, black body, attraction force, based on the gravitational, you can use this mass to do the calculation, actually. It's quite fun. Okay. This actually also explained why the, you know, how did we prove the Einstein gravitation, general relativity in 1930 something? Is we have this Earth, so we observe the sun full solar eclipse, and so we were saying that we shouldn't able to see a star behind the sun because it's blocked. However, we were able to see it in 1930 something, prove that many scientists at a different place of the Earth trying to observe a star just blocked by straight line, blocked by sun, behind the sun, but under the full eclipse, we actually able to see that. And so really means the light coming from this guy actually was bended. Yeah. That's why we were able to see. And the bend actually is because the gravitational force between the sun and the photon, which can calculate this way. So people are asking why photon has no mass, no static mass, photon can feel the sun gravitational force in general relativity. It's because it has this dynamic mass. So you can still apply the gravitational force to light, to photon. Okay.
Did someone like detect the sort of like bend in light like a couple of years ago and got a Nobel Prize?
Yes. So that was you are talking about the gravitational wave. You know, the two of the black hole collide together, generate huge space time warp, and which is gravitational you know, wave propagating towards Earth, and we were able to detect that.
Okay.
That's another 100 years later to another strong proof of Einstein theory. Okay.
Wait, that was very recent.
That is a few years
27.
ago. Yeah. Okay. So this is basically the black hole and the formula. And now let's get again, doing physics, you're about dealing with number, and you have to get a. So let's write down R black hole critical radium equal to T2 black hole mass divided by C squared. Okay, this formula. So let's see. This is quite interesting, actually. Let's see. So we know. So for Earth to turn into a black hole, which is this. So really means we know the Earth's mass is 6 times 10 to 24 kilogram. Okay. We know the G constant 6.67 10 to minus 11 Newton square, meter square, kilometer. So in that case, if we use Earth, which is so heavy, turn into a black hole, so how we need to, basically the question is, we need to squeeze of Earth to how small Earth become a Earth, I mean cold, by cold, become a black hole. Do that calculation, try. So that is basically saying, that is basically R equals to 2 times 6.67 10 to minus 11 times 6 times 10 to 24. So let's check the units are correct. Okay, Newton meter square kilogram minus 2, that's from gravitational constant. So then we time the kilogram from Earth unit here, those two units time together, and divided by C squared. C equals 3 times 10 to power 8 meter per second. So therefore it's 9 times 10 to 16 meters squared second minus 2. Correct? Okay, so you can see I will cancel out the meter square cancel out, kilogram cancel out 1 kilogram. I still have 1 kilogram down. So basic kilogram down here. And so I still have Newton here. So I will rewrite everything. So this one, if you do this kind of this number, so that becomes roughly 9 times 10 to minus 3. Okay, this converted into Newton. The rest of them becomes Newton second square divided by kilometer. I just want to confirm the unit is correct. Okay, has to be a meter. So this one unit becomes because Newton is F equal ma, means kilogram times meter per second square. That is Newton times second square divided by kilogram. So you can see that it is meter, right? So therefore, it becomes 9 times 10 to minus 3 meter, which is what? 9 millimeter. So this is just for fun, right? So this is saying Earth from this size, Earth is how big? Earth has a radius about 64,000 kilometer, has to squeeze into 1 centimeter, or 2 centimeter, because it's radium. So 2 centimeter size. It's like a marble piece, this size. Earth squeeze into this size, it will become black hole. Amazing? This is a black hole. So really means the black hole is so dense, so heavy, and so small. I mean, not necessarily so small, but it's so heavy in order to be able to become a black hole. So that's why the nothing can escape. Because you're moving, because in the Earth's case, you cannot, if you move to the center of Earth 2 centimeters from the Earth's center, then it's nothing. However, if you squeeze the Earth's whole mass into 2 centimeters, you are moving 2 centimeters, 3 centimeters away from that center. You feel all the mass, gravitational force from this size of mass within 2 centimeters. So that is why you are crashed, your light being crashed, cannot escape. Okay, so this is where we are. Okay, go back quickly, take one more time look. And now let's continue this just fun. Okay. Let's do a little bit play. So what if here we are assuming the mass, the Earth's mass kept, and we just squeeze them and until become black hole, and then you have to squeeze into 2 centimeters, right? Less than an egg in order to turn it into a black hole. But can we keep the Earth the current way density? Earth's average density is about 5.5 gram per cubic centimeter. I think that is. I believe that is. Let me see. Let me check. I think that is Earth's. Yeah, I think this is Earth's current average density. Okay, so if we keep Earth's current weight, do not squeeze it, and can we turn Earth into a black hole? We call the density constant. Yes, you can, but you have to keep adding more stuff. You have to basically Earth. You have to keep adding something, same density material until one day it become a black hole. So let's do that calculation. How? So we already know the black hole, the radium is black hole's radium equals to black hole radium equals to 2gmc squared. Okay, that is one thing we need to use. And meanwhile, we know the density equals to mass divided by volume, correct? Right? So really means for a sphere divided by volume is 4/3 pi r cubic, correct? So that is then you will see it's interesting. What you see is that from here you see that r equals to cubic root of 3m 4 pi rho. Yes. So you see for a normal, for any sphere, the radium's increase with mass as a constant density is by a cubic relationship. However, for black hole, radium increase with mass by linear relationship. So at a certain stage, those two can come cross. So basically, let's draw it. So this is mass. This is the radium, So for black hole is a linear, right? So this slope is basically 2g divided by c squared is a slope, right? So mass increase, black hole linearly increase diameter. However, for the regular sphere, the relationship between the radium and mass is going to be a cubic this. So at a certain size, it crosses over. So this is this curve. This is this curve. So, but where is this crossover point? So how big Earth needed to grow into in order to meet the criteria, increase, meet the criteria, become a black hole. So that basically leading to these two formulas saying, so that's 2gm divided by c squared equals to cubic root of 3m divided by 4 pi rho, correct? So that give you 8g cubic m cubic divided by c power 6 equals to 3m 4 pi rho, correct? So that give me cancel out, become 2. That give me mass equals to square root of 3c power 6 divided by 32 pi rho g cube, correct? Here to here. So if you so that give you c power 6 3 4g square root of 3 2 pi rho g. Right, that's just simple math. And then you put all the number in. You know the c is a 3 times. You know the c number, g number, and you know the c number, g number, and rho number. Rho is 5.5. Rho for Earth is 5.5 gram per centimeter cube. And you put everything in. Make sure your unit is unified. This is not SI unit. You have to convert into kilogram, meters cube, right? Convert into that one. Put in the back, and everything use international unit. Eventually, this one come to, if you calculate, it come to 1.14 10 to 38 kilogram. That's so this when Earth at a current density keep increase mass on hitting this mass, then it turn into a black hole according to the black hole relationship, black hole mass relationship. So this is how much. This is basically this new mass divided by Earth's mass equals to 10 to how many billion of Earth until it can hit the black hole requirement. Or we have another way to look at is basically is go back to calculate R. So in this case, how big the Earth going to be? So it's gmc squared. Put the mass into here. So you do the calculation. That's 10.67, 10 to minus 11 times 1.14, 10 third 8 divided by c squared, 9 times 10 to 16. So this one eventually come to 1.7 10 to 11 kilometer. How big this one is, this guy is. So when we keep adding mass and Earth become bigger until it becomes a black hole at the current density of 5.5 gram per centimeter cube. In that case, Earth has to be this size, gigantic size, This size is how big, give you idea. So basically compared to 3 number. So our current Earth radius is 64,000 kilometer, right? So it's basically 6 times 10 to power 3 kilometer, right? Here's 10 to power 11, okay? And now our sun size is about 150 million kilo. So that's 1.5 10 to 8 kilogram. So this 10 to 8. But here is 10 to 11. So sun size is still too small. And one AU, which means Earth to sun distance, we call an astronomy unit, which is 1.5. Oh, sorry. So Earth is a meaning, it's 10 to 6, sorry. So 1.4, 10 to 6. This one is 10 to 8. So it's still, so basically when Earth expanded the current density until we reach sun, we are still several orders smaller than the requirement to become a black hole. So our whole sun solar system, our solar system's radium. So basically, sun is here. The furthest one from our solar system is about 1.4 10 to 11. So this is roughly. So basically, our Earth has to be expanded, keep expanded until becomes a whole solar system. Our solar basically reach to the cover all the 9大行星, right? Expanded to basically to be from current place and cover the whole solar size, our solar system size. So then it roughly become a black hole. So this is a universe. This is talking about the black holes. Give you some idea, just using some of our what we do. Any question? I don't know if this sounds fun or not, but I thought it's good to know.
Yeah, Dr. Wang, the results are always super interesting. The math in the middle, sometimes we're like, oh, there's so much math in the middle, but then you get to the number and it's really cool.
Yeah. Of course, I skipped something of the calculation, but you are derived. The only thing, make sure when you derive those numbers, right? No matter what number you do the calculation, and always make sure your unit is correct. Okay. So unit has to be consistent. For example, when you use in a row here, you cannot just use 5.5 because your unit is not correct. But the rest is kilogram or meter and or second. You have to use the same SI unit. So that's the only thing. If you pay attention to that, you shouldn't make much difficulty to do this kind of quick calculation. Okay.
Yeah, thank you.
Just make sure the unit okay. Okay. So then before we finish here today, I'd like to give you another idea. So if we want to turn sun into black hole, you can do the same calculation because sun's mass is 2 times 10 to 30 kilogram. And then once you do, you will get sun will become 3 kilogram in order to, sun will become roughly the central Manhattan size in order to become black holes. You have to squeeze. Sun is currently a helium, a hydrogen ball, and of course, it's a nuclear reactor. You have to squeeze the sun into a 3 kilometer diameter, and so that give you a turn sun into a black hole. And so that gives you some idea. Okay, you can do a quickly calculations this way. So now the next is a very interesting question. So our observable universe, scientists find our observable, we will define this one later, observable universe mass is about 1.46 10 to 53 kilogram. Okay. Huge. This is our observable universe. If you use this one to follow the black hole formula, R equals to 2 gm divided c squared, you put this number in and you calculate. So this one becomes you can calculate, become 4 point, I think is 2, roughly 2 times 10 to 26 meter. And eventually you convert it into light year. You have to divide the, you know, the light, 1 year light travels the distance. So that one converted into, I think is 20 some billion light year. 20 some billion light year. So if you do this, actually our observable universe is roughly this size.
Wait, does it mean that the whole universe is a black hole?
Yeah. So so our observable universe is like a black hole.
But does universe have infinite boundary or like finite boundaries?
Yeah, that's a question. Really, I'm saying it's observable universe. We don't know, right?
Okay.
So
Nobody knows.
What does it mean observable universe? There's another conversation. It's a pretty complicated conversation. It involves the Big Bang. So remember our universe is only 13.7 billion year history, correct?
Mm-hmm.
So basically we are only 13.7 billion year. But how could our observable universe right now is 46 billion light year? That's very confusing. So how our universe is only 13.7 billion year? How could we can observe a 46 billion light year observable universe?
Do we observe through light, like through sight, or through like other parameters?
Through light. Nothing can travel faster than light.
Wait, if we like observe the universe through light, then how do we like observe the black hole since there isn't any light coming out from it?
Oh, we are inside the black hole. We are not outside black hole.
Huh.
Huh.
But still, like, how did human know the existence of black hole if there isn't any light coming out from it, and we perceive everything through light?
Yeah. So that's a good question. Actually, a couple years ago, MIT and those group remember there's you Google it. There's famous black hole picture.
Yep.
There's black hole picture, correct? Yeah.
The egg.
Yeah. So black hole pictures. So what do you say that picture?
Like a ball.
It's a black hole. I mean, just around it there's light, but the inside there's black.
Mm-hmm.
It doesn't contradict what we said. There's nothing can escape, but that's why that part is black.
Yeah.
But away
So
from
just observe the ring
so
around
basically
it.
saying this side is black, is nothing can come out. But what can come out is outside this diameter, this radius. This side is light. This side.
And then we assume that instead of like the middle being empty, we assume that there is like a huge chunk of mass in which light cannot come out.
Correct.
Okay.
So actually the essential contradictory here sounds to anyone is if the universe is only 13.7 billion years, so light in the flat universe can only travel 13.7 billion light year, correct?
Mm-hmm.
Beginning of the universe, universe. So how could you have 46 light year away stuff? So anyway, that's a future discussion we can get. It's quite interesting, actually. Just talking about universe and talking about the whole thing. And I also want to go back talking about light speed, because nothing can travel faster than light speed, which is only like this. So in that case, you know, we are here, sun, a little bit away from under the universe scale. We are Earth, sun, and so the nearby another star which is like sun. What is it? Do we know? Do anybody know the nearest star to us? How far away?
Alpha Centauri was like.
Yeah, how far yeah, exactly. And how far that one is?
I think it's 4.9.
Yeah, something about 4 light years away. So light needed to travel 4 years from there to us. Right? That is the closest one we have. Then we have then everything by light year. So then we can easily have thousands light year away, millions light year away, billions light year away galaxies. And so therefore, when we're standing on Earth or standing on sun, looking out into universe, what do we see?
We see the past.
Yeah, we see the past, right? We see this star is 4 years ago. Then any moment that we receive in the night, we see this star. We know it's not now, at this moment, what happened. It's 4 years ago what happened. Exactly 4 light year ago what happened. Then if you look further, another star which will be 10 light year, 100 light year, million light year. So for the million light year, if we are able to see it, so what we see is 1 million year ago what happened with this place. But no now. What happened now? We don't know. We have no way to know, because the light is still on the way, hasn't reached to us, right? So this is a big picture of the universe. It's quite interesting. So we look into the sky, we look into a past. We look into the edge of the universe, we look into the beginning of the universe, starting of the universe, because that is certain of some light year away, billion light year away. We looking into our past, universe past. And so that is the whole concept we need to be in mind, okay? So that is amazing, right? We will never be able to look at what happened, to know what happened of the whole universe at this particular moment. There's no way we know that. We only depending on how big the circle away from us, depending on a light year, 1 light year, million light year, billion light year. So we see every layer, which is further older, longer time away from us. So that is we observe. But that is our limit. We have no way to break that limit, at least based on current scientific understanding, right? So that is everything is basically fixed by the light speed, because no information can pass faster than light. No anything can pass faster than light speed of at least communicate information. So therefore, there's no way we know what going to happen. So the reason we see observable universe is that meaning coming from observable universe, meaning coming from beyond a certain circle from Earth. We know light will never reach to us. Even we can go over infinite into the future, light will never go get to us. This is because another principle called expanding we call Hubble constant. That is another discussion. Okay, but here's you know, so that's what we talked today, and sorry I'm run over time again, and so I hope you enjoy a little bit, and I know there's lots of numbers here, and but it's not too complicated physics here, and but you have any question, let me know. Okay.
Mm-hmm.
Good.
Yeah. Thank you so much, Dr. Wang.
Okay. Yeah. I hope
Thank you.
Yeah, able to enjoy.
Thank you, Dr. Wang.
Yeah. Okay. Talk to you later. Bye bye. I will send the recording if you want to watch later. Okay. Bye bye.
All right. Thank you.
Bye bye.